Hello and welcome to the talk on the full potential linearized augmented plane wave method. My name is Gregor Michalicek and I will present this topic to you. So, in detail, I will give you first an overview on the theoretical background of the method. So there we will learn about the LAPW basis and its different extensions. I will also show you how the core electrons are treated differently from the valence electrons, and I will briefly discuss how the density and the potential are represented. Then I will show you how the input files to Fleur actually look like, and there we will also see how the parameters we learned about in this first theoretical section transfer into actual inputs to Fleur. And finally, I will give you a short list of suggested further reading, and then I will conclude my talk. So let us directly dive into this theoretical background. But before we discuss this LAPW basis, let me give you a brief reminder on how the electron wave functions actually look like in a periodic solid. So at low energies, the electron wave functions are actually pretty localized, and there we are talking about so-called core electrons. If we go to higher energies, the wave functions are more and more extended and get more and more nodes, and at some point we are talking about so-called semi-core electrons, and at even higher energies we are talking about valence electrons, and there the wave functions are very extended and have many nodes, or can have many nodes. So of course the representation of these valence electrons has to comply with the Bloch theorem. So it means that we have to have some factor of some Bloch phase with some periodic functions uk of r. So let us have a look at how the LAPW basis actually covers such a representation. And in this description, we actually have a partitioning of the unit cell in so-called muffin-tin spheres around each atom and an interstitial region in between these muffin-tin spheres. So in this interstitial region, the representation consists of plane waves, and there we already see this Bloch factor and this periodicity. And in the muffin-tin spheres, the representation consists of these radial functions times spherical harmonics, and these radial functions are the functions u and u dot, and these are actually solutions and energy derivatives for the spherical potential at certain energy parameters, EL alpha. And we also have there these A and B matching coefficients, and they are actually determined by enforcing continuity in value and slope of the basis functions for the respective L channel. So we already have some parameters that enter this description. So the most important one is K max, and this is actually the reciprocal plane wave cutoff that determines the basis set size. So if you have a look at this plane wave in the interstitial, this K max actually determines how many of these plane waves enter our basis set. And then there is also some L max parameter, so this is an angular momentum cutoff for each muffin-tin sphere, and this determines up to which L the sum in the muffin-tin sphere goes. Of course, these muffin-tin spheres can have different sizes, and for this we also define some muffin-tin radius, and this is R muffin-tin alpha. And of course, this muffin-tin radius is not always the same. It depends on the material and on the chemical bonding and so on. Finally, there are also these energy parameters. So these u and u dot functions are determined at certain energies, and we somehow have to define these energy parameters. So we use this LAPW basis to represent the valence electrons, and for this LAPW basis has to be orthogonal to the core electron states. And here I will briefly sketch the proof that this actually is the case. And in this proof we will see that certain assumptions enter, and this is something that you should keep in mind. So consider that you construct the wave functions, the U from the LAPW basis or the core electron wave functions you will see by some radial Schrödinger equation that we have here. Yeah. Then what we do, we multiply this radial Schrödinger equation for UL by R times ULC, and the Schrödinger equation for ULC by R times UL. And then we subtract the two resulting equations from each other and we integrate over the Muffin-Tin sphere. And we end up with this equation that we see here below. And what you see here immediately is that these red terms, so the angular momentum barrier and the effective potential, vanish because they are in both equations and they cancel each other. And on the right hand side we actually already have some scalar product times some energy difference. So this is the energy difference between the energy parameter and the core electron state eigenenergy. And of course this is finite, but what we want to show is that this scalar product becomes zero. And for this we have to evaluate the left hand side of the equation, and of course it's not directly obvious what this will give us, but if you do some integration by parts or if you apply Green's second identity, you will end up with two terms that become zero if the core electron wave function and its radial derivative vanish at the Muffin-Tin sphere boundary. So these are actually assumptions that have to enter this proof, and of course I did not show you this integration, but this is something that you have to keep in mind. So then you see that on the right hand side we have this scalar product again, and left hand side becomes zero. So U is orthogonal to ULC, and analogously you can also show that UL dot is orthogonal to ULC. So this orthogonality actually allows us to determine the core and valence electron energies and wave functions separately from each other. So, and what we do is we treat the core electrons for each atom separately on some radial mesh, and we do this in a fully relativistic treatment. And the valence electrons we describe by the LAPW basis. There we have a scalar relativistic description of the Muffin-Tin spheres, so this is something that actually differs from what I showed you before. So before we saw the radial Schrödinger equation, but in reality this is a scalar relativistic description. And optionally we can also include spin-orbit coupling. But keep in mind that for this treatment to work in the way we want it to work, we have to have this condition that the core electron wave functions vanish in value and slope at the Muffin-Tin sphere boundary, but this is only approximately fulfilled, and for semi-core states this fulfillment may not be good enough, and then we may get some ghost bands, and this may lead to problems. So there we have to pay attention. So one more aspect about the LAPW basis that you have to keep in mind is the linearization. So consider that we want to describe some state at an arbitrary energy epsilon. We can expand the state in terms of a power series around the energy parameter EL alpha. Yeah, and then you see we have this term with the UL and we have this term with the UL dot, but we don't have higher order terms. So actually what we have is a good description in the neighborhood of this energy parameter, but if we go farther away from this energy parameter, our description gets less and less good. And this description is actually good enough to get accurate results for many materials, but there are also some cases where this description is not enough, and for example, if you have very broad bands with large Muffin-Tin spheres, you will see that you could use an improvement of this description, but there is a solution to that, and we will see this later. but you should also keep in mind, of course, this representation in the muffin-tin spheres is not improved by increasing this reciprocal cutoff parameter k max that we use for the plane wave. Yeah. So, sorry. So there is a way of overcoming this linearization error that we have due to this linearization, and this is the addition of so-called local orbitals. And these local orbitals look like this. So we also have these functions u and u dot that we already know from the LAPW basis, and we have an additional function u in this case, and this is just the conventional u evaluated at a different energy parameter, EL, LO. And these local orbitals are mainly used to describe semiconstates, and you see that we also have these coefficients A, B, and C in this description, and they are all actually determined by enforcing zero value and slope at the muffin-tin sphere boundary of this local orbital, and also some normalization of the function. So, and what do we do with that? So we can describe semiconstates with that, and for this we use semicollocal orbitals. There we choose the energy parameter such that it is in the near of the semiconstate. We can also describe unoccupied states with so-called higher energy local orbitals, and there we choose the energy parameter above the Fermi energy somewhere within the range of the unoccupied states. And we can also in generally improve the description of the LAPW basis around the energy parameters by not choosing a u but a u double dot, so a second energy derivative evaluated at the same energy parameter as we use for the LAPW basis functions. So there is another extension to the LAPW basis, and this is not an extension in terms of additional basis function, but we can also cover different geometries, and for example film setups. And film setups are two-dimensional, but we have a certain thickness of the film, and above and below the film we have vacuum regions. And in these regions we have a description similar to what we have in the muffin-tin spheres, so also some functions u and u dot evaluated at certain energy parameters, and some matching coefficients a and b, so that we have a continuity in value and slope at the vacuum boundary. And of course, we already saw that this film has a certain finite thickness that is determined or that is provided as the parameter d, and there's also a parameter d tilde that you will see in the Fleur input, and this is actually a slightly extended film thickness that we use for the determination of the lattice vectors. And then there are also the the vacuum energy parameters for the determination of this u and u dot functions. So now let us briefly discuss the representation of the density and the potential. Analogously to what we have in for the wave functions, the density and potential also have a plane wave part, and so this is some conventional plane wave expansion. And we have some muffin-tin part, which consists of radial functions times spherical harmonics again, and actually it is slightly more complicated because we don't use plane waves, but we use so-called stars, and these are symmetrized plane waves that actually already have the symmetry of the unit cell that we want to describe. And similarly for the plane wave description, we don't have spherical harmonics but lattice harmonics, and these are also symmetrized functions. We have new parameters here. So the most important is G max, and this is the reciprocal plane wave cutoff for the density and the potential. And of course the expansion in the Muffin-Tin sphere also has an Lmax cutoff parameter, and this is the same that we use for the LAPW basis. So let us go to the input files to Fleur, and there you have to know that of course we don't want the user to provide every parameter on their own, and but we want to support the user in doing that. And for this we have a scheme where we first use an input generator, and to this input generator we provide very basic structural input on the unit cell. And this input generator then generates a Fleur input file that has default values for all these parameters that we saw in the last minutes. So an input to input imgen looks like this. So we first have some command line, and here is this command line says that we are have an input for sodium chloride bulk, and then we have to define the lattice somehow. So this is an FCC lattice that we want to describe, and with a lattice parameter of 10.62 Bohr radii. So this is something that you have to keep in mind. We provide all inputs in terms of Hartree atomic units, so this means lengths are measured in Bohr radii. So then we say that we have two atoms in the unit cell. The first atom is sodium at 0, 0, 0, and the second atom is chlorine at 1/2, 1/2, 1/2. So we use the input generator by invoking intgen with -f to indicate the input file, and here the input file is called myInputFile.txt, but it can have every name you want to give it. You can also invoke it with the option -h, and then you will see a list of command line options that you have, and some of these command line options provide additional parameterization in the Fleur input file. For example, this -noco switch also gives some default parameters for non-collinear magnetism input. So this input generator then creates a Fleur input file, or an imp.xml file, and this imp.xml file looks like this. So it consists of several sections. First comes the comment again, then there's a calculation setup section with different general parameterizations, then there's a cell section that defines the unit cell and also the reciprocal cell. Then there is an atom species section and an atom group section, and finally there's an output section. And if we want to start Fleur with this, then we just have to invoke Fleur or Fleur_MPI, depending on what executable you actually have. And of course, if you start Fleur with the command line option -h, you will also see a display of all the options that there are. So the calculation setup section looks like this. We have the parameterization there of the Kmax cutoff, the Gmax cutoff, and other cutoffs, and then we can also control how the SCF loop is processed, so the number of iterations of the SCF cycle, or some convergence criterion, or we can define how the core electrons are treated. We can set the exchange correlation functional, so in this case this is the PPE functional. We can say whether we want to have a magnetic or a non-magnetic calculation, so in this case this is non-magnetic. And then there's the cell section, and first thing we have to define there is the number of valence electrons, so in this case it's 16. And we also define there some smearing for the occupation function. Then we have to define what list of k points we want to use. So we can have different lists in our input, and here we select the list by a certain name. And next, the lists are actually included, and they are typically stored in this external file kpts.xml. And then in a similar way, we also include the symmetry observations that are typically stored in the sym.xml file. And finally, we have to define the Bravais matrix for the unit cell. This you see here. So this is a conventional FCC like unit cell. So next comes the atom species section. So each species has a name. So in this case it's sodium underline Na, and it also has an atomic number, of course. You have definitions for the muffin sphere, including the radius and so on. And you see the atomic cutoffs, like this Lmax cutoff, and also some reduced cutoff for the inclusion of the contributions due to the non-spherical potential in the muffin spheres. And then you have to set the electron configuration, and there you have to define which states are treated as core electron states. So in this case this is a 1s state, and which states are treated as valence electrons, and in this case this is a 2s, 2p1/2, 2p3/2, and 3s. And for each state that is not fully occupied, you also have to define how the occupation looks like. So the 3s 1/2 state features 1/2 spin up electron and 1/2 spin down electron in this case. Then you have to specify the energy parameters, and this is specified typically in terms of main quantum numbers. So we want to represent 3s electrons and 3p electrons, 3d and 4f. And we can also define several local orbitals here. So in this case there are two local orbitals for semicore states, and the first one is for the 2s, so n equals 2 and l equals 0 is s state, and for the 2p state. Next comes the atom group section, and there the atoms are actually grouped according to their symmetries. So symmetry equivalent atoms are will be placed in the same group, but of course in this example we don't have this, but what we see is the positions of the atoms. So sodium is at 0, 0, 0, and chlorine is at 1/2, 1/2, 1/2. And the important thing here is that each atom group is connected to one of the species that we saw before by specifying the species name. So then comes the output section, and there we can actually control the output of Fleur and parts of the calculation. There we can, for example, say that we want to calculate a density of states by setting this DOS switch to true, or that we want to calculate a band structure by setting this band switch to true. And we can also say, for example, what the energy window on which the DOS is plotted looks like. Yeah, so it goes from this min energy to this max energy relative to the Fermi energy. And finally, there's another file included, that is the relax.xml file, and this may be there or not. It typically includes some atom displacements, and so it may happen that you do some structural relaxation and then the atoms gets displaced, and for this we don't change the entries that we already saw, but we add additional information in this relax.xml file. And if this relax.xml file is present, the atoms get displaced, and if it's not present, they don't get displaced. So let me show you some more output files and also input files. So we learned about imp.xml, sym.xml, and kpts.xml. There also is some optional definition of or alternative definition of the energy parameters for which you can provide an para file. Then depending on whether you compiled Fleur with support from the HDF5 library or without HDF5, you get different charge density files. So cdn.hdf contains the charge density, or without HDF5 is cdn1 and so on. And I mark here the HDF files in green because they typically include some additional data that make the usage of Fleur more comfortable. Then you may also have some output on the mixing history. So if you want to, if your calculation did not yet finish after these 15 iterations or so, then you want to restart the calculation, and a part of the data that you can use there is in the mixing history, but you can also delete it if you think that the mixing history is not useful. But you will always start from the last density that you calculated. So of course you can also have additional input for special calculations, and the main output files are the out file and the out.xml file. They contain mostly the same information. The out file is made for humans to read, and the out.xml file typically for automatized processing, but it's also very readable for humans. And if we do density of states calculations or band structure calculations, you get some output on the respective data. And if you compiled if you compiled Fleur with HDF5, you get this additional file band.hdf, and this actually includes some additional data, like for example ways that are related to the projection of your states onto certain atoms and so on. So here's a short list on suggested further reading. So you can have a look at this overview book by Singh, or you can have a look at the initial publication by Anderson. You can have a look at the extension of FLAPW for thin film systems, or how the potential is calculated in FLAPW, or also an interesting read maybe on the augmented-plane-wave method, so the predecessor by Slater. And also local orbitals may be an interesting read, and so there's an initial publication where the local orbitals were invented by Singh, and they were used for treating semi-core states. And then we have some publication for these higher energy local orbitals and for the higher derivative local orbitals, and there's actually also some publication by me with an analysis of the linearization error. Yeah. And now let me conclude the talk. So I showed you about the LAPW basis, and we discussed the local orbitals and the linearization error. I showed you how the LAPW basis looks like for a film setup. We discussed the different input and output files, but there were also some things that we did not discuss, and this was related to how we choose the parameters. But there will be another talk on this. And with this, let me thank you for your attention and enjoy the rest of the workshop. Bye bye.